This is Physics Lab 4, analyzing the motion of this spring as it oscillates in two directions. Essentially what's going on here is the spring is let go from rest and allowed to move, and we are supposed to computationally model in Tracker and VPython what it is doing, based on the ideas of Newton's second law and some energy principles. Starting from Newton's second law, that F net equals ma, we have two forces in this situation. We have the spring force, given by the spring here, and the force due to gravity, given by the Earth, where gravity is equal to ma, mass times the acceleration due to gravity, and the spring force is equal to k, which is the spring constant, which you can calculate for a given spring, multiplied by s, which is how stretched out the spring is, and that's given by L naught, which is the relaxed length of the spring, it's sitting on a table, minus the current length, which is, that's L. So L naught minus L is equal to F. Essentially, is that given an accurate measure of the period, you can get a very, very accurate model of the motion of the spring and the object. So, this is how I measured the period. Essentially, this is the this is the end of the fourth period of oscillation, and this is the end of the first period of oscillation. So there are three between them. And so you divide by 3, and you get 1 period's length. The spring constant k is given by 4 pi squared times mass divided by the period squared. L naught is equal to 0.7, which is the length when the weight is just hanging, like that. So that's 0.7 meters from there to there, there to there, minus mg over the spring constant. L, which is just the length of the spring at any given time, is equal to the spring position, which is this fixed point, minus the mass's position, which is this point. So, like, that's L there. L hat is the unit vector in that direction, and S is the magnitude of L minus L naught, because L is a vector and L naught is just a distance. Then the energy-related stuff that we use later on. So the change in energy is just equal to E final minus E initial. Kinetic energy is equal to 1/2 mv squared. Gravitational potential energy is equal to mgh, where g is, again, the gravitational acceleration, and h is the relative distance above Earth. So, like, you don't need the exact distance here, you just need, going from sort of our origin, you just need, oh, this one is lower than that one by some distance. And so that's that. And then spring potential energy is 1/2 kx squared, or 1/2 ks, where s is this value squared. Okay, so running the code, you get this. And some things to take note of. These are following the same path, it's just offset by about a quarter of a period. You can see that much more clearly here, where this is just motion in the x direction. They're following almost the exact same path, it's just offset by a period and slightly different magnitude. And then over here, we have the graph of the changes in energy. So blue is the change in kinetic energy, green is the change in spring potential energy, red is the change in gravitational potential energy, and yellow is the change in total energy. And the first thing to notice is that there is no change in total energy. The change in total energy is 0, which means that total energy is constant. What that also means is that given that you have, say, spring potential and gravitational potential, the difference between them is going to be kinetic energy. So, like, if you summed up spring potential and kinetic at any one point, you'd get gravitational potential, and so on and so forth. So, essentially, the sum of any two, the sum of all three is equal to 0, right? That makes sense. And the reason for that is, if we go over here, because, as this first question asks, the energy principle is satisfied. And the idea behind that is that since there is nothing adding or removing energy from this system, right, there is no, like, heat or thruster or any kind of thing that's being converted into additional energy. There's no external force on the system. There's nothing like that. The total energy is constant, and because of that, the change in energy is going to also be not only constant, but 0, if you think about it like a derivative. And so that's why you get this. And because of that, the energy principle is satisfied. Clearly. Okay. So, now, I said before, if you looked at the oscillation, if you looked at the visual of the oscillation, they followed almost the same path, just offset slightly. So now I'm going to show you a different one, because the other question asks, given the data you obtained, make two versions, one using a period based on the x and one using a period based on the y direction, and compare the two. So I just showed you x before, and this is y. And as you can see, they don't actually follow the same path here. They're actually doing completely different things. What's going on there? We're not quite sure. And if you look on this graph here of their motion in just a single direction, in the x direction, you can see that they're not following the same path. Whereas on the first example, the peaks and troughs stayed the same distance apart. In this case, they aren't. There's movement between them, and the red one is, quote-unquote, catching up to the blue one. So they're not actually following the same period. And because of that, the first model with the period that's closer to 1.6 is significantly better. And do note, I calculated both in the same way